this video, we're going to talk about Gibbs free energy. So Gibbs free energy is the maximum energy that's released by a process. And the process has to be at constant temperature and pressure. And also the energy has to be available to do useful work. So Gibbs free energy is a way of relating enthalpy and entropy, which are the two variables we've already talked about. So remember, enthalpy is kind of like the heat change for a reaction. That's the way we tend to describe it. And entropy is the amount of disorder. So free energy relates enthalpy and entropy as well as the temperature for a given process. So far when we've talked about whether something is spontaneous, we've said that generally, if something is spontaneous, there's an increase in entropy, meaning the system becomes more disordered, so delta S is positive, or in other words, greater than 0. And we've also said that things tend to be spontaneous if the process is exothermic, meaning delta H is negative or less than 0. So we can relate the enthalpy, the entropy, and the temperature using the equation for Gibbs free energy. So the thing that actually matters, that's useful to us, is that the change in Gibbs free energy, so delta G, is equal to delta H minus T times delta S. So, we've talked about with delta H and delta S when things are spontaneous. What about with delta G? So for delta G, if delta G is less than 0, the reaction is spontaneous. If delta G is greater than 0, the reaction is non-spontaneous. And if delta G is equal to 0, the reaction mixture is at equilibrium. So we have a table here that relates everything. So we have delta H, delta S, and delta G. So the first one is the conditions we've already talked about. We know that when enthalpy is negative, that a reaction tends to be spontaneous. We know that when entropy is positive, a reaction is spontaneous. And we just said when delta G is less than 0, a reaction is always spontaneous. So if you have something that has a negative delta H, a positive delta S, and a negative delta G, the reaction is going to be spontaneous. Now, these are not the only times a reaction can be spontaneous. This is probably the most straightforward way for it to be spontaneous, but there are other situations. So remember, the formula is delta G is equal to delta H minus T delta S. And we want delta G to be negative. So we're subtracting T delta S from delta H. So if you have a situation where delta H is negative, so a negative delta H would be spontaneous, but if that exothermic reaction actually becomes more ordered, then delta S would be negative. So delta S being negative, you would think that that's not spontaneous. If delta T is low enough here, if delta H is already negative, and delta T is small, then even if delta S is negative, a negative times a negative is a positive, so we would have negative plus something. So essentially this term here would be adding to delta H. But if T is small enough and this term is small enough, then delta H is large enough that delta G will still be negative. So even if delta S is negative, at lower temperatures, the reaction is still spontaneous because delta G is still less than 0. Now, what if we have the situation where delta S is positive, which should be spontaneous, but delta H is positive, which would not be spontaneous. So again, if we take our equation, delta G is equal to delta H minus T delta S. Even if delta H is positive, we're subtracting this term. If delta S is positive, if T is high enough, then this term here becomes large enough that delta G will still be negative. So if both delta H and delta S are negative, the reaction is only spontaneous at lower temperature. If both delta H and delta S are positive, the reaction is only going to be spontaneous at higher temperature. If we have the situation where delta H is positive, which we know is not spontaneous, and delta S is negative, which we also know is not spontaneous, there's no way mathematically that works out to be less than 0. So if delta H is positive and delta S is negative, then delta G is going to be greater than 0, which means that situation can never be spontaneous. So if you're unsure, if you're given delta H and delta S, you can plug those in and calculate delta G, because delta G is what's going to tell us overall if the reaction is spontaneous or not. So let's try a calculation here. Iron metal can be produced with water as a byproduct by reducing iron 3 oxide with hydrogen. This reaction has a delta H equals positive 98.8 kilojoules and delta S equals positive 141.5 joules per Kelvin. Is the reaction spontaneous at 25 degrees Celsius? At what temperature will the reaction become spontaneous? So the first question asks us if the reaction is spontaneous at 25 degrees Celsius. So let's do the algebra here, and let's see if delta G is negative. So delta G is equal to delta H minus T delta S. So we have a delta H of 98.8 kilojoules. Need the pen here. Kilojoules minus T, 25 plus 273 gives us a temperature of 298. And delta S is 141.5 joules per Kelvin. So T is 298 Kelvin. So Kelvin cancels with Kelvin here. And we have 98.8 kilojoules minus, if we take 298 times 141.5, that comes out to 42,167 joules. But as I mentioned earlier, we have delta H in kilojoules and delta S in joules. So we need to convert one of them. So I'm going to go ahead and convert delta S to kilojoules so that delta G will be in kilojoules. So if I divide 42,167 by 1,000, I have 98.8 kilojoules, minus 42.167 kilojoules. So if I subtract that, I get 56.633 kilojoules, which, if I keep the correct number of significant figures, rounds off to 57 kilojoules. So this is positive 57 kilojoules. So no, at 25 degrees Celsius, the reaction would not be spontaneous. So the second part of this question asks us, at what temperature would the reaction become spontaneous? So I'm going to add another slide here. Let's see. New slide. And we want it to be blank. So if we go back to the question here, we want to know at what temperature we can make this spontaneous. So we know that delta G has to be negative for the reaction to be spontaneous. Now, it doesn't need to be negative a certain value, it just has to be negative. So what we're going to do is say delta G is equal to 0 and calculate at what temperature that would happen. Now, if we know at what temperature delta G would equal 0, if the temperature is above that temperature, then this T delta S term is going to be larger than the delta H term, which will make delta G negative. So we can calculate where delta G would be 0, and we know that anything above that would be negative. So let's go ahead and plug in. We have delta G is equal to delta H minus T delta S. And we're going to calculate the temperature at which delta G equals 0. So we have 98.8 kilojoules minus 141.5 joules per Kelvin. And we need to get temperature by itself, so I'm going to add the T delta S term over to the other side so that I can work towards getting T by itself. And I'm left with 98.8 kilojoules on this side. And then I'm going to divide both sides. So that gets rid of my delta S and gets T by itself. So I said 98.8 kilojoules, 141.5 joules per Kelvin, but I know I have to convert joules into kilojoules. So if I take 98.8 and divide that by 141.5 divided by 1,000, that comes out to 698 Kelvin, or if I convert that to Celsius, 425 degrees Celsius. So the reaction would become spontaneous above 425 degrees Celsius. So you will see sometimes if you look at these equations, or if you look at delta G or delta H or delta S, you will see this little symbol that looks like a degree symbol. And we pronounce that not. So we call it delta G naught, delta H naught, and delta S naught. What these little symbols refer to is it's telling you that those values are measured or calculated at what we call standard state. So the thermodynamic standard state is the most stable form of a substance at 1 atm of pressure and at a specified temperature. So usually we're specifying 25 degrees Celsius. And if we're talking about something in solution, it would have to be a 1 molar concentration. So standard state is defined as 1 atm of pressure, 25 degrees Celsius, and a 1 molar concentration for anything that's in solution. So let's look at a calculation where we have everything at standard state. Calculate the standard free energy change at 25 degrees Celsius for the Haber synthesis of ammonia using the given values for the standard enthalpy and standard entropy changes. So we have delta G, so it's the same equation except we're using the symbol for standard state. So delta G naught is equal to delta H naught minus T delta S naught. So if we plug in our delta H naught and our T, so 25 plus 273 gives us 298 Kelvin. And then our delta S naught, so we have negative 198.7 joules per Kelvin. So we know that Kelvin will cancel with Kelvin, since we have Kelvin on the top and Kelvin on the bottom. So we can simplify the end of this, 92.2 kilojoules minus 298 times 198.7. A negative times a negative is going to be a positive. And if we multiply those two together, we get 59,213 joules, but we want to convert that to kilojoules. So if we divide that value by 1,000 and then take negative 92.2 plus 59,213 divided by 1,000, you should come up with negative 33.0 kilojoules. We can also calculate delta G for a reaction if we're given delta G for the products and delta G for the reactants. So, just like for enthalpy and entropy, we did products minus reactants. We do the same thing for delta G. So we always take, whether we're doing delta G, delta H, or delta S, we always take products minus reactants, and we have to take into account how many moles of the products and reactants we have. So let's take a look at an example. So here's a table that shows some of the values for different substances, and you also have a table in the appendix of your book. So using the values given in the table, calculate the standard free energy change at 25 degrees Celsius for the reduction of iron 3 oxide with carbon monoxide. So if you were to look this up in a table, or if you look back at the table we have here, delta G for Fe2O3 is negative 742.2 kilojoules per mole. Delta G for carbon monoxide is negative 137.2. Delta G for iron would be 0. And delta G for carbon dioxide is negative 394.2 kilojoules per mole. So to calculate for the reaction, we take, if we start on the product side, because we do products minus reactants, we have 2 moles of iron, which has a delta G of 0 kilojoules per mole, and we have 3 moles of carbon dioxide. We have delta G equals 394.2 kilojoules per mole. And then we can subtract off the reactants. So we only have 1 mole of iron 3 oxide here. And it has a delta G of negative 742.2 kilojoules per mole. Plus, there's 3 moles of carbon dioxide, and that has a delta G of 137.2 kilojoules per mole. So if we take 2 times 0 is 0, so 3 times negative 394.2 minus negative 742 plus 3 times negative 137.2. If you plug all that into your calculator, you should come up with negative 29.4 kilojoules per mole. So, delta G will give us the direction of a spontaneous reaction. At standard state, it will tell us whether or not a reaction will be spontaneous. But what about if we're not under standard conditions? Well, we can calculate what delta G would be if we're under non-standard conditions. So the equation for that is delta G is equal to delta G naught plus RT times the natural log of Q. And remember that Q is an equilibrium constant when we're not at equilibrium. Now, R is not the one that we use for the gas law. In this case, the R that you're going to need is the 8.314 joules per Kelvin times the moles. So delta G, when it doesn't have the naught symbol there, is the free energy change under non-standard conditions. Now, a lot of times when we're calculating Q, we'll have reactions in the gaseous state. So for gases, sometimes it's more convenient to use partial pressures instead of concentrations. So if we were writing this in terms of concentrations, we would write Q is equal to NH3 squared over N2 times H2 cubed. We can do the same thing with partial pressures, except that we square the partial pressure of NH3 instead of the concentration. We have the partial pressure of N2 instead of the concentration, and we cube the partial pressure of H2 instead of its concentration. So we just have partial pressures there instead of molarities. So let's take a look at an example where we use this equation. We want to calculate delta G for the formation of ethylene, which is C2H4 from carbon and hydrogen at 25 degrees Celsius when the partial pressures are 100 atm for H2 and 0.10 atm for C2H4. So let's start by writing the expression for QP and doing the calculation. So QP is when we're using partial pressures. P is equal to the partial pressure of C2H2 over the partial pressure of H2 squared. So we have 0.10 divided by 100 squared. So if we take 0.10 divided by 100 squared, we get 1 times 10 to the negative 5th. So now we can plug into our equation delta G naught delta G is equal to delta G naught plus RT ln of Q. So delta G naught we can get from a table of standard values. And if you look up the delta G naught for the formation of C2H4 from carbon and hydrogen, you will find out that is 68.1 kilojoules per mole. Plus we have R is 8.314 joules per Kelvin times moles times the temperature, if we convert that to Kelvin, is 298 Kelvin, and we have the natural log of 1 times 10 to the negative 5th. So if we take the end of our equation here and simplify it, we have 68.1 kilojoules per mole plus 8.314 times 298 times the natural log of 1 times 10 to the negative 5th gives us negative 34,229 joules per mole. But we need to convert this to kilojoules, so we have 1,000 joules per 1 kilojoule. So if we then divide this value by 1,000, we have 68.1 kilojoules per mole plus a negative 34.2 kilojoules per mole. And if you add those together, you should get 40 kilojoules per mole. So, we can calculate delta G if we know delta G is standard state. But what about if we're at equilibrium? Well, if we're at equilibrium, then delta G would be equal to 0, and Q would be equal to K. So remember, K is our equilibrium constant when we're at equilibrium. Q is the value we can use when we're not at equilibrium. So if we are at equilibrium, then this equation becomes 0 is equal to delta G plus RT natural log of K, since we're at equilibrium. And then we can algebraically rearrange this to get delta G naught by itself. So at equilibrium, delta G naught is equal to negative RT ln of K. So if we have our equilibrium constant, we can plug in R and the temperature in Kelvin and calculate delta G naught. So, how can we relate those to which direction a reaction will go? Well, if delta G naught is less than 0, which means the reaction is spontaneous, and K is large, remember if K is much greater than 10 to the third, then we favor the products. So when delta G is less than 0, it's a spontaneous reaction. When K is large, we favor the products. If delta G is only slightly negative, K is still going to be greater than 1, so we slightly favor the products, but not as heavily. We don't have as large of a K, so we're still going to favor the product side, but we're still going to have a noticeable concentration of reactants when we're at equilibrium. And if we have the situation where delta G is greater than 0 and K is much less than 0, then our reaction favors reactants. So we would still be mostly at reactants with just a small amount of products. So let's look at a couple of examples here where we have to use that equation. Calculate K at 25 degrees Celsius for the following reaction. So we're given a reaction here and we're given delta G of formation for each of these elements, or for each of these compounds that are in this reaction. So we have delta G is equal to, we do products minus reactants. So calcium oxide, there's only 1 mole of it. So we have negative 604.0 kilojoules per mole. We also only have 1 mole of carbon dioxide, so we can plug in the value for carbon dioxide, and then we can subtract the value for calcium carbonate, which is negative 1028.8 kilojoules per mole. So if we take negative 604 plus a negative 394.4, and then minus the negative is positive, so plus 1128.8, we get 130.4 kilojoules per mole. So then we can plug that into our equation. We have delta G is equal to negative RT ln of K. So we just calculated delta G, so I'm going to rearrange this equation and get the ln of K by itself. Since I already have delta G. So the natural log of K is equal to, we calculated 130.4 kilojoules per mole for our delta G. And we have 8.314 joules per Kelvin times mole. So R is in joules, but we need it in kilojoules because delta G is in kilojoules. So I'm going to go ahead and put a conversion factor in here. And then T was 25 degrees Celsius, which is 298 Kelvin. So if we put all of this in our calculator here, and we need to put a negative sign here because this is negative RT. So 130.4 divided by negative 8.314 divided by 1,000 times 298. And press enter on that, we get negative 52.6. So the way that we get rid of a natural log, the inverse of that is e to the negative 52.6. And if we take e to the negative 52.6, we get 1.4 times 10 to the 23rd for our value for k. So this is another example where we do exactly the same thing. So I'm going to let you try this one and see what you come up with for the value of k. So we will stop here and we will get some more practice with calculating Gibbs free energy and looking at the relationships between Gibbs free energy and enthalpy and entropy and K and Q in class. So I will see you in class.